So in today's lesson, I'm going to be talking to you about two concepts, solubility and solubility curves. So first, before we begin, I want to gauge your understanding of what it means to describe a solid's solubility. So something that is highly soluble, what does that mean? Well, let's just imagine that I have a certain amount of solution here, and I have an equal amount of, I'm going to say, solvent here. So let's just say that both of these are, have water in them, right? An equal volume of water. Well, a substance, a solute that has a high solubility means I can take a whole lot of that solute and expect that it's all going to dissolve to make a one-phase solution. Whereas, so this is, our high solubility situation. But if I have a situation where my solute has very low solubility, that means that if I were to add the same amount of that solute to water, well, what would I see? I would see that probably a little small amount of it might dissolve, but the rest I would see as a precipitate on the bottom of my beaker. So that's sort of my understanding of solubility. Let's look at it in more specific terms in terms of chemistry. So in chemistry, we talk about solubility as describing the amount of a substance needed to make a saturated solution at a given temperature, right? So for instance, I could be measuring the solubility of a substance in grams per 100 grams of water or grams per 100 milliliters of water. I could also be measuring it in moles per liter. But essentially, it's describing, I'm going to draw my little beaker here again, what it's describing is remember that amount of a substance, that solute that I was adding? It's describing the maximum amount of that solute that I can add to a given amount of water and have it actually dissolve, the maximum amount. So in other words, if I were to add just a tiny little bit more of that solute, it would precipitate. Okay? So remember that a saturated solution is a solution where I've added the maximum amount of solute at a given temperature and no more can be added. So for instance, if I were to describe the solubility of a particular solid as being, let's say, 25 grams per 100 milliliters of water, what that would mean was that the maximum amount of that solid that I could add to 100 milliliters of water would be 25 grams. And if I added 26 grams of that solid to the solution, well, what would I expect to see? I would expect there to be a 1 gram precipitate at the bottom of my container. So, for example, if I were to look this up at a given temperature, the solubility of sodium chloride, that's just regular table salt, is 35.7 grams per 100 grams of water, right? So what that tells me is that if I had 100 grams of water, for every 100 grams of water, the maximum amount of sodium chloride I could expect to dissolve would be 35.7 grams per 100 grams of water, right? So if I had a different volume of water, right, let's say I had 200 grams, well, how much sodium chloride could I dissolve in 200 grams? Well, 2 times 35.7 grams, and right, per 200 grams, and so on and so forth, right? So, in general, and this is just sort of a way for us to kind of create a bit of a scale. In general, we say that a solubility of below 0.1 moles per liter is considered low solubility, right? So if all I can dissolve is 0.1 moles of that substance, that solute per liter, that means I can't dissolve a whole lot. So I would say that substance has very low solubility. Whereas if I'm able to dissolve 0.1 moles of a solute for every liter or greater, that means that substance is considered to have a high solubility. All right, so this is kind of the cutoff, the 0.1 moles per liter. Well, let's look at how we could go ahead and take that sodium chloride value and figure out whether that is a high or a low solubility. So the first thing I would do is I would say, well, if I have 35.7 grams per 100 grams of water, then I know that I have 357 grams of sodium chloride for 1,000 grams of water. And we know that the density of water is 1 gram per milliliter. So if I have 1,000 grams, that also means that I have 1,000 milliliters, and that's what a liter is. So, that's the first part that I would say here. Now, the second thing that I would say is this. Is that now I know that there is 357 grams of sodium chloride per 1,000 milliliters, which is per liter, right? So if I know what my mass is per liter, I can certainly figure out what my number of moles are per liter. My number of moles is equal to my mass, 357 grams, divided by the molar mass of NaCl, which I believe is 58.44 grams per mole. So let's work this out. I can tell already that that's going to be a pretty high value. So 357 divided by 58.44. So this is telling me that I have 6.11 moles per liter. So we know that sodium chloride is pretty soluble in water. We know that from our everyday experience. But we can see here that, in fact, 6.11 moles per liter of it can dissolve, which confirms that indeed it is highly soluble because its solubility is way above this, 0.1 moles per liter concentration. All right. So now that we have an understanding of solubility, I want to move on to talk about what is happening when a solute dissolves. So I want to remind you that when we take an ionic solid, so in this case I've chosen lead iodide. I know that for every lead iodide particle that dissociates, I'm going to produce one lead ion and two iodide ions, right? I've got the PbI2, so if I go ahead and I dissociate these into ions, my ratio is, there's going to be one lead for every two iodide ions, right? So that's what's happening when an ionic solid dissolves. And so, what I can do is I can use stoichiometry to help me make some predictions about the ion concentration that might be present in solution, right? So let's say, for instance, if I know that I have 0.1 moles per liter of lead iodide, my 1:2 ratio of lead iodide to iodide ion, my 1:2 ratio tells me that I should expect to have double that amount, 0.2 moles per liter of my iodide ion present in solution. So that can be useful. Okay, now, so here's an example that I would like for you to try out. So let's try this out first. Okay, so the first part of this is I want you to write out an equation for the dissociation of calcium phosphate. So pause the video and give that a try. And when you're ready, resume the video and we can check how you did. Okay, so the key to getting this done properly is to ensure that you are getting the formula for calcium phosphate written out properly. So I know calcium phosphate has the formula Ca3PO4 bracket 2, and that is because calcium has a 2+ ionic charge, and phosphate, the phosphate polyatomic ion, has a 3- charge. So then I'm going to go ahead, I'm going to dissociate that. I'm going to start by writing out each ion with its ionic charge, so Ca2 plus and PO4 with a 3 negative charge. And you can't leave those out because it is an ionic dissociation. So without those charges there, you haven't done it properly. Now I'm going to go ahead and I'm going to balance. Well, I have 3 calciums here, which means that for every 1 calcium phosphate, I'm going to be releasing 3 calcium ions. And for every 1 calcium phosphate, I have 2 phosphate ions that are dissociating and become free in solution, so I'm going to put a 2 there. So hopefully you did okay with that. Let's look at the next part of this question. So the next part of this question is as follows. Oopsies, I've got that a little bit. There we go, that's a little bit better. If 44 micrograms of calcium phosphate are dissolved in 1 liter solution, what is the molar concentration of, I'm going to guess, calcium ion? Yeah, calcium ions. There we go. All right. So I want you to pause the video and give that a try, and then come back when you're ready, and we will check out the answer together. All right, so the first thing I'm going to do is I'm going to remember that in order to get molar concentration, I'm going to need to get, the number of moles per liter. So I somehow need to get my micrograms into moles, and then my liter is already in liters, so I'm good to go. So really the only thing I need to do is to take these micrograms and somehow figure out how many moles that is equivalent to. The first thing I'm going to do is I'm going to remember that, 44 micrograms is, I have 1 microgram is equal to 10 to the negative 6 grams. So I'm going to get that conversion right. So 4.4 times 10 to the negative 5 grams. That's what I have there. So now that I have that correctly converted to the right unit, I'm going to go ahead and calculate my moles of calcium phosphate. So my number of moles is equal to my mass divided by my molar mass. So I'm going to cheat, and I'm going to look up the molar mass of calcium phosphate. So mine might differ slightly from yours, but that's okay. And so when I look up the molar mass of calcium phosphate, I am getting 310.18. So I'm going to go ahead and include that. So 4.4 times 10 to the negative 5 grams divided by 310.18 grams per mole. Giving me to 2 significant digits, 1.4 times 10 to the negative, let me count those zeros, 6, 7, negative 7 moles per liter. Okay, so remember, I can say that it's moles per liter. Why? Because in the original question, it told me that I had exactly 1 liter of solution. So there's my molar concentration of calcium phosphate. So now I'm almost done because I haven't figured out what my molar concentration of calcium ion is. So my final step is going to be to say, well, if I have 1 mole per liter of calcium phosphate, then I'm going to liberate 3 moles per liter of calcium ion. So in order to get my molar concentration of calcium ion in solution, I need to look at my mole ratio. So I'm going to give myself a little bit more space here. Let me move all of this up. And so my third step is going to be to say, well, I have 1.4 times 10 to the negative 7 moles of calcium phosphate. But there's 3 calcium ions for every 1 calcium phosphate. So essentially I'm just tripling that, so times 3. So that gives me 4.2 times 10 to the negative 7 moles per liter of calcium ion. And I'm done. All right, let's move on. All right, so the next thing I want to just mention really briefly, and I think it will make sense, but I want you to think about it. So the greater the solubility, okay, the greater the conductivity in an electrolyte solution. So, for example, if I have an ionic solid, let's say I have two ionic solutions. I'm going to draw, here's one beaker, and then here's another beaker, right? And in this first beaker, which I'm going to call beaker A, and then this one is beaker B, but in beaker A, let's say I have a bunch of sodiums and a bunch of chlorides. Here's, another chloride, another sodium. So really high concentration of ions, right? Let's just assume. Versus in solution B, let's say I have maybe just very few ions. Well, you'll remember that electric current is basically just moving charged particles. And so if I'm trying to connect some kind of, let's say I had electrodes in this, you'll remember that we had this connected to a circuit before, and we had a little light bulb, right? If I'm trying to conduct in solution, and there are lots of moving particles, lots and lots of moving particles that can carry charge, well, that's going to allow my circuit to work a whole lot better. It's going to be much more conductive. As opposed to a solution with very few moving charges, it's not going to create a very good current, very strong current, and so the conductivity of solution B is going to be very, very low. So in essence, the greater the number of charged particles, right, that are able to move freely, the greater the conductivity. So in other words, the higher the solubility, the more ions I'm able to put in solution as moving charged particles, the better that solution that I've created is going to be at conducting charge. So the next topic that I want to talk about is solubility curves. And so a solubility curve is basically a graph that measures the concentration of a solute in solution. And notice the units here are in grams per 100 milliliters. And so that describes the grams of my solute per 100 milliliters of solvent. And I'm measuring that as a function of temperature. So as you can imagine, for most solids, as you increase the temperature of your solvent, usually that's water, right? So in other words, the hotter the water, we can see a general trend here that the more solid we can dissolve. So for example, if I wanted to know how much, I'm going to use potassium nitrate here. I'm going to use potassium nitrate. If I wanted to know, well, at 40 degrees Celsius, how much potassium nitrate could I expect to dissolve? Well, I'm going to follow my line up to see my graph to see where it is that it hits the graph, and then go across here and measure, right? So that's what's going to tell me that at 40 degrees Celsius, let me see, 4, it looks like I can probably dissolve about 64 grams of potassium nitrate at 40 degrees Celsius per 100 milliliters of water, right? So I have my 100 milliliters of water here. That means that of my potassium nitrate, the maximum amount that I could dissolve without seeing a precipitate in the bottom would be 64 grams of that potassium nitrate. So anything above that would create a saturated solution, and I would see a precipitate in the bottom. And if I added less than that, I would have an unsaturated solution. All right, so let me get rid of some of this, and then we'll talk a little bit more about solubility curves. So a solubility curve essentially is telling you, based on the substance, how soluble it is in solution. So I'm going to give you an amount here, and you're going to tell me that if that amount of solute at a given temperature is put into solution, whether I should expect that solution to be saturated or unsaturated. So here is the scenario. I'm going to say NaCl. So let's say I put 30 grams of NaCl in 100 milliliters of water. Will that be a saturated solution or an unsaturated solution? Take a minute, pause the video, and give this a try on your own. All right, so, I forgot to tell you what temperature. That's probably pretty important, right? So I'm going to tell you that at, let's say at 60 degrees Celsius. All right, so I'm going to go ahead and tackle this problem. So 30 grams in 100 milliliters at 60 degrees Celsius. So I'm going to follow my 60 degrees Celsius line up to 30 grams per 100 milliliters. And that I'm hitting right here. And so since the maximum amount of sodium chloride at 30 degrees Celsius would be higher than 30 grams per 100 grams of water or milliliters of water, that tells me that there's actually an amount here that I could add more, right? There's a discrepancy here. I can add a number of grams more than 30 grams. So that tells me that this solution right here would be unsaturated as I've described it, so unsaturated. Okay, so let's try another example. I'm going to get rid of some of this, and then we'll see how you do. Okay, so next problem. I'm going to make this a little harder for you. I'm going to choose, in this case, I'm going to choose NH4Cl. And I'm going to tell you, let's describe NH4Cl at 80 degrees Celsius. And I want to know if I add 80 grams in 200 milliliters, whether it will be saturated or unsaturated, this solution. Okay, take a minute, try this out, and then give the question a try, and we'll come back together and discuss. Okay, so first of all, I need to recognize that on my graph, the label in this case says grams per 100 milliliters. So I can't really use this graph until I have considered that reality, right? And so going back to my units here, my information that I'm given, I know that if I have 80 grams for 200 milliliters, then, I know that that would be 40 grams per 100 milliliters. So I need to consider that. So let's take a look at where that lies on my graph. So at 80 degrees Celsius, I'm going to follow my line up, 80 degrees Celsius. And when I look at this graph right here, I can see that looks like it's about 246-ish. So it looks to me like that is 66 grams per 100 milliliters. The maximum amount of ammonium chloride I can add is 66 grams per 100 milliliters. Since I'm only adding 40 grams per 100 milliliters, that tells me that the solution that I'm describing would be unsaturated. So hopefully you did okay with that. So overall, all of these are ionic solids. And so what do we see as the trend for ionic solids as temperature increases? Well, all of these lines, without exception, show an increase in solubility as temperature increases, right? So for solids, it's fair to say that as we heat up water or we heat up our solvent, we're going to be able to dissolve more solids in that solvent. right? So for most solids, that happens to be true. The solubility will increase with temperature. Just think about washing dishes in cold water. If we're trying to do that, and I know I've done that camping, and it's really annoying, trying to wash dishes in cold water just takes more effort and time than if I wash in hot water, right? That's because some of those solids that are maybe stuck on your plate just don't dissolve as well in that cold water, just because of molecular motion. Interestingly enough, though, gases have the opposite property. So as you heat up a solution, gases are going to want to dissolve less in water. So think about that with your carbonated beverage like Pepsi, Coke, whatever, right? If you have your Coke or your Pepsi that's really, really cold, you're going to see that it's going to taste like it has more carbonation. Whereas if you heat up, or you have a Coke at room temperature and you open up the container, a lot of the carbon dioxide is easily going to be able to escape, and it's going to taste a lot more flat. Another good example of how this applies is if you're fishing, and I'm not sure if anybody likes to fish here, but there are certain fish that like to live, sort of closer to the surface of the water, where the temperature of the water is a lot warmer, whereas other fish have to live, further down, closer to the bottom. And that's because the water happens to be a lot colder there, and so there's going to be a whole lot more dissolved oxygen there. So depending on the oxygen demand, so let's say, for instance, down here, maybe this is, 10 degrees Celsius. Maybe down here is like maybe minus 10 degrees Celsius. And because of the lower temperature, there's going to be more oxygen down here. Maybe this particular fish requires more oxygen to survive, and so maybe there's less oxygen at a higher level up in the water, and so this fish maybe requires less oxygen to survive. But also maybe depending on the season, a fish can survive at different positions within the water levels, depending on what the temperature is, what the climate is at that time. So I'm going to be posting some particular homework that I want you to try out from your textbook that I think will help you to gauge what your understanding is of solubility and solubility curves and your ability to interpret data from solubility curves. So I'm going to strongly encourage you to follow through on that work today and make sure that you are able to work through it successfully. And if you have any questions, make sure that you bring those to the table tomorrow at the beginning of class so that we can sort them out.